Okay guys, the next quick thing which I'd like to discuss is also very important. It's this matter of the next point in the textbook is on equilibrium. And what we saw is that as we begin to apply our force P, I want you to notice two things here. As you begin to apply force P, two things happen. Number one, a frictional force develops. So if there's no P, there's no frictional force P, no applied force P, then the frictional force is 0. Okay? So that's number one. Let's write it down. As we apply P, two things happen. Frictional force develops. Okay? And number two, that normal distribution, which we discussed in the first video, that normal distribution begins to shift to the right. The concentration begins to shift to the right, and that normal force is no longer just merely opposing W, it is moving to the right. And I want you to take note of that little value X, and that the normal force is to the right. So the normal force shifts. I don't really want to say shifts to the right because, because many of you students are gonna memorize this, right? You're gonna say, okay, shifts to the right. I need to memorize that. Shifts to the right, shifts to the right. And then I give you a problem where the applied force is to the left, and you're still gonna shift the normal force to the right. Okay? The normal force, we'll see now. Just take note that the normal force shifts and a frictional force develops as we apply P. All right? Now, to understand this, well, we've already understood the frictional force here from this diagram, this 1C, that as we apply the force, we have these reaction forces which are stopping the top block from moving relative to the bottom surface. And that all those reaction forces have a normal component and a horizontal component. That horizontal component is then the frictional force, and the normal component obviously is the normal force, and it shifts to the right. Okay, but let's do now an equilibrium. Let's look at the equilibrium equations, and let's look at the free body diagram. We've got the weight, got the normal force P. This is just fundamental. The background, this is quite important for us in terms of analyzing the problems later. And there's our frictional force. Okay? And there's a distance x. Now, let's see what is required for this block to be in equilibrium. Remember, and we'll do some problems later, if you recall from class, the block can either slip or it can tip. In terms of moving, right, or non-equilibrium, or going out of equilibrium. So what is required for it to be in equilibrium? Well, let's look. So the sum of the forces in the x equals 0. So we've got P minus F is 0. So you can see as I apply P, F is reacting to that force P in order to keep it in equilibrium. Sum of the forces in the y equals 0. Normal minus W is equal to 0. So that one we've known from since we were in grade 1 or grade 2, that the normal force opposes the weight. But then the other important one which we need is the sum of the moments about, let's take a point about there, let's call it A. Sum of the moments about A equals 0. You can take moments about any point in the universe, doesn't matter. But let's take points about that point. Why would we do that? Simply because we want to cancel these ones out, right? So we want to simplify it. So we take moments about A, we get W, right, that weight times that moment arm, Wx minus, and let's make that H for height, imagine that, minus P times H, right? And so we took anti-clockwise as positive. So W is going to cause an anti-clockwise moment about A, and P is going to cause a clockwise moment about A. We set that equal to 0. Now I want you to notice something. this equation here essentially is telling us that as we apply P, this P wants to rotate this box, this object, this structure about that point. It wants to rotate it like that. But then what's actually happening is, and I know it's maybe not so clear there, but this normal force is also reacting against that P. So P is applying a moment like that to want to tip this box, and this normal force is applying a reaction moment in the opposite direction. I know it doesn't say N times X, okay, but N is equal to W. So essentially that is the same as NX, all right? So again, as we apply P, it wants to tip the box in a clockwise way, and this normal force then wants to react in order to keep it in equilibrium, in order to keep it in rotational, let's put it that way, rotational equilibrium. Okay, we have this opposing moment N that's caused by the force N that opposes this applied moment. Okay, and what you should notice, let's rewrite it. How about we take moments about that point there? Let's call that point O. All right, it's essentially the same thing. If we take moments about point O, again, we're going to get N times X. That's an anti-clockwise moment. So we're going to N times X, and we're going to get a clockwise moment minus PH. Right? It's essentially exactly the same thing because W equals N. Okay. Now, as you apply P, it wants to cause a clockwise moment about that point. But then we have N that wants to cause an anti-clockwise moment about that point in order to keep the box in equilibrium. Now, if we solve for X, this is quite important. Solve for X, we get PH over, now I'm going to go back to this one, okay, over W. N equals W, you can just interchange them, all right? So what we need to see here is that X, that distance from that center of the box to the applied that reaction, the normal force, sorry, that X is that distance there, and it is a function of P. As we increase the applied force P, as we increase this P, this normal force keeps shifting to the right. It keeps shifting to the right. What is that normal force doing? Number one, it's counteracting the weight, obviously, but why is it shifting? Because it needs to counteract that moment. As that moment P, as the moment caused by P gets larger and larger, N times X must get larger and larger to counteract that applied moment. So X then is a function of P. As P gets larger, X gets larger because N keeps shifting more away and away from that point there to counteract the moment. As we increase the height of P, X also increases because the moment is increasing, okay? And then if we increase the weight, then it reduces X. So X would then go back there. So I want you to please just to take note of this, okay? And what ends up happening is, for tipping, right, which is when we do not have rotational equilibrium, as we keep increasing P or H, whichever one, X keeps increasing because this normal force keeps moving to the right to increase the counteracting moment, okay? And the maximum that it can go is up until that point, obviously, right? It can't move any further. So as the minute that X moves, the minute that X is larger than that distance, we are going to have tipping. All right? So I hope that's just kind of opened up a little bit of this idea of slipping and tipping. Slipping, we will get to it in a minute. That's impending motion. We will look at that in the next video. So this box can move in two ways. It can slip And that's essentially related to this equation, right? It's this one here. And tipping is essentially related to this equation there. So slipping is a translational, okay? And tipping is rotational movement. Okay, so I hope this is cleared up a bit. I did repeat myself a lot, but I hope it makes sense. Cheers.